Hello everyone, this is the next episode of our recordings of Dotty internals. This episode is going to be mostly about denotations, and if we have some time later, we'll also cover how to debug typer. Okay, so denotations. Previous recording added on named types, which Martin intentionally put last, because they're the part where most of the fun stuff happens. So a named type is something which is a selection from a prefix with a given name. So if you have, let's say, an object A which internally has a type B, then you can build a type which stands for A.B. Or you can build a term which stands for A.C. So named type is a superclass of two types, the term ref and the type ref. Type ref refers to a type, so it's defined by a name inside this prefix, while term ref is slightly more complex. Because we have overloads, term refs may need a signature. So term ref has several more subclasses. Term ref with signature and term ref with fixed sim. Term refs with signature is needed when method is overloaded, and term refs with fixed sim is needed in more tricky cases when you literally want to pin and refer to the specific symbol. It happens quite rarely. In most cases it happens where you don't have a name or a type yet, but you already created a symbol for it, which you can rename later. So now, after we've created this term ref, it doesn't actually say what it means. We need to figure out what's the meaning of this name inside this prefix. And that's what denotations are. So denotations track a meaning of something at a given time. Let's start with the time. If you recall from the very previous recording, we had a notion of period. So inside compiler we can track time frames. We have phases that create phase IDs, which are indexed inside this period bits, and we have runs. Additionally, runs are different runs of compiler. So the denotation indicates what's the meaning of a specific name, a specific run, and at a specific phase. It's very helpful to do this because it's common for the same name to mean different things. For example, let's take a method bar, which takes a t as a type parameter and has two argument strings. So before erasure, this method bar will look like it's a polytype which returns a method type which takes a single argument, which returns a method type, which takes an int, which returns the right hand side, which let's say will be double. The same method, when we approach erasure, would first be uncarried, so it won't have multiple arguments, and then it will stop being polymorphic. So though you're referring to the same method, you're referring to the same name, it means different stuff, even during the same compilation run. It can also happen that it can change the meaning not because it's being transformed by compiler, but because it has been edited by user. So for example, you're now in the next run, and user has modified this method to return an int. You want to be able to correctly handle all the cases which used to refer to this method and understand they now refer to a different signature. All this logic of correctly handling changing of the meaning is isolated in denotations.
So can I ask what the meaning of a meaning is? So specifically, are you talking only about the type of the method, or does the symbol also change? Because you're still talking about the same method, just with a different type?
So symbols aren't guaranteed to survive across runs. Symbol may have
Okay.
changed, symbol may have stayed the same, but you shouldn't rely on them staying. So if you want to have something stable between runs, name type is your best bet.
Maybe you should define what a run is.
But okay, but in your example of the bar method,
Yeah?
so we're within a single run, but in different phases.
Mm-hmm.
Does the meaning include the symbol that it's still the same bar method, or do you get different symbols in different phases?
You are very likely to get the same symbol in different phases, but you're not guaranteed to.
Okay, so then the meaning is relates to the type of that method.
So
Is there anything else in the meaning that is other than the type?
it's also the symbol, as you said correctly. So you can have the same name, which used to refer to one symbol, and now refers to a
Okay.
different symbol. So
Okay,
denotations are indexed by period, and so denotations form a cycle. Let me find this to you. Next. Next.
right.
Maybe it's hard to
So-
give an example.
Yeah, no, I understand that you get different denotations in different periods.
Mm-hmm.
What I'm asking is what is all the information that a denotation tells you?
So denotation tells you a symbol if it has a symbol. There are denotations which don't have a symbol.
Okay,
And it does tell you the type. So the most precise thing that it tells you is a type.
okay,
Additionally, it can tell you whether the thing exists in the first place. So denotation may
Okay.
say that it stopped existing.
okay, okay,
So yeah, so here's this
Okay.
method called, well, protected field called next in run, which is used for a denotation to refer to the next meaning of the same name in the next period.
right, okay,
So
okay,
denotations through this field formed a singly list circular list, a circle,
okay,
where every next in run is next phase, and then it goes back to the first one.
okay,
This is the origin of how time travel works in Dotty. So in Dotty, you can ask about it for a meaning of anything at any specific period. And what it does is all the APIs ask denotations to convert themselves to a meaning at this specific phase. So this records the versioned history of how everything looked at every particular phase in the past, and they will record how it will look in the future. So the method initial is a helper method in particular, which tells you when did the thing first start existing.
okay,
And it returns you this very first thing in the cycle, which has the slowest phase ID when it exists. To make it slightly more optimal, we simplify this list by checking that if denotation didn't change much, didn't change at all, and you're returning the same denotation for a future phase, we'll merge them. So now, how do denotations get changed? We have denote transformers. Denote transformer is something that takes previous denotation. Single denotation means that it means a single thing. There may be denotations which means multiple things, which internally are comprised of single denotations. So you're transforming what previous single denotation stood for, and you're returning what it will stand for now. To give you an example, let's say we have elim repeated. So before phase elim repeated, some methods could have had repeated arguments. After elim repeated, they won't. So the meaning of their name should get transformed to indicate that they no longer have repeated arguments. It also indicates that they no longer override Java stuff, because we'll need to add bridges, and now the bridges will override stuff. So with this method transform gets called from. Okay. IntelliJ decided to stop working.
Switch to cloud.
No, it did actually fine. It just took forever. So there is this method denotation.current, which is called from all the places which try to recompute the denotation. Which, in case you're asking for a meaning of a denotation which has not been yet computed, it will get the next denote transformer and call it. So you see, you get this next. Then it checks if next has the same meaning as the current, then it will update it so that the previous one, so that it spawns more phases. This allows us to maintain denotations that don't change much and don't create much garbage. Yeah. So there are complex cases which denotations have to handle. The most complex case happens when you go across runs. If you go across runs and you have denotation, you don't know if your prefix still exists in the first place. You more or less know nothing. So in order to do this, to handle this case, it tries to find the first denotation that you ever have had defined, and it tries to bring this forward. So bring forward method is responsible for bringing a denotation into a new run, or saying that it can't do it. This is used in separate compilation in case we have multiple. We reuse the compiler for multiple iterations compiling the same code base. The most common use case for this is IDE. So if you're in IDE, every time you type a new character, you have a new run. Every time it tries to type check it and give you error messages, it brings forward all existing denotations as much as it could in order to not recompute them. Okay.
Does it bring the form?
Sorry?
Does it go through? Does it bring when a new run kicks in? Does the compiler bring forward all the denotations in a lazy manner, or does it go through all of them and bring them forward?
So bring forward is called from current. All the operations and denotations are lazy, all of them.
Okay.
Even symbol loading is more or less handled through denotations. Denotations start with init.info. So the denotations start with a type. One of these particular kinds of types is lazy type. This is our completers. So we start by registers top level symbols for everything that we find on the class path. That will have these lazy types as their types, and they will change themselves and they will force themselves when we touch them. If we don't touch them, they don't form themselves. Formally, there is one case where this framework nicely falls apart, and that happens if the period run ID overflows. So if you had a denotation which you last touched more than 2 to the 17th to the power of 17th runs away, you could think that this denotation is valid when it's still not. Yeah. Okay, so that's how denotations work internally. Denotations are the foundation of Dotty in a sense that they are inside everything. Types in the end refer to the named types, which store the last denotation inside the named type. So if we take, for example, term ref here, okay, key maps here are different. It stores the last denotation as a fast path in order to make it faster. But if the last denotation is incorrect, so denotation is not current, the named type will reload it, asking the denotation to update itself. If it can't update itself, it will try to recompute it given the prefix that it had from last symbols and stuff. Last symbols are most common. You have a denotation which has a last symbol but not a denotation only in typer. you have a named type which has the last symbol but not denotation only in typer during the very first bootstraps of things when you don't have right owners yet. But after you're more or less typing something, everything should have a correct denotation set and everything should go without using symbols inside the name types. Okay, now, as was said, they're transformed lazily. So it sometimes becomes tricky to debug them, both because they can execute, they may not execute by the time you want them to execute because they're lazy. So finding bugs in denotation transformers, for example, Java standard library is quite hard because depending what you do in Java standard library, you may not touch the same things, or you may touch them earlier than you planned. In particular, when I was saying here that we need signature, so if I have term ref, when you have an overloaded method, may need a signature. This signature is an erased signature. So you're building a reference to a type in a typer, but you already need to figure out what is signature, which kind of means that you have to erase it. This more or less suggests, and that's what actually happens, is that typer runs info transformers up until erasure, because he needs to understand what's going to be the erased signature of it. What else? So now, how do you use this stuff? Denotation transformers are a right place to introduce new definitions, new members, new methods, new classes. They are a right place to change existing definitions. If you want to change what do they stand for, or maybe get rid of them. It is possible to forcefully change them from the phase itself, but if you do this, you're mutating the history which has already been recorded and may have been observed by somebody else. There is an API to do this. The entry point method is transform following. Now, enter it after. So if you want to enter stuff, the entry point will be entered after. You're saying that something should start existing after a specific denote transformer by doing it forcefully instead of doing it the right way by transforming existing things. And also, let me find where was the method. Transform after. Yeah, and you also have a method called transform after, which says that you want to transform all the future meanings of the denotation. The thing is, you may want to forcefully change an existing denotation which already has a future. And if you're very careful, you may know how to update this future. For example, if you're changing the owner in the past, that's very likely that you want to change the owner consistently in the future. Normally, that's not something that you want to do, but that's how low-level APIs are implemented. So in particular, change owner after works this way. Okay. Now, with denote transformers, it's important to understand that the trees that's being transformed, the types being transformed may not be tree defined. So when you're deciding how to transform a method or a type or a symbol, you should think whether you need to transform it only if you're currently compiling it, or you want to also transform it if it has been compiled as your dependency and you're compiling against it. Denote transformers is your only way to transform something that has been registered in the class path or something that comes from Java, because you won't have trees for those. So in short, if you can use denote transformers, that's the most reliable way to transform symbols. but you'll have to mimic what they do in the face because the face has to make the tree consistent with it. In practice, Denote transformers are quite rare. So most Denote transformers are very simple and they do something very small and easy to understand. Let's say normalize for...
Can I just ask about your last point about transforming or doing the consistent transformation in the tree?
Yep.
So if you transform the tree, is there ever a place where the denotations or the types and then the denotations get recomputed from the tree? Or do you have to mirror every transformation that you do to the tree in the denotation transformers as well?
So when denotation transformer changed the meaning of a tree or of a name, you are responsible on updating the meaning of the actual tree in a face. If you have updated it in a face, it's being checked against what it should stand for from point of denotation transformers. So you have to implement both if you're changing public signatures. Okay. So yeah. If you're changing local signatures, let's say you're changing inner methods, it's actually perfectly fine to do it inside the method, the tree transformer, because you won't ever be able to observe it outside of the class. But if you're changing public signature, you want to be able to know, you want to be sure that when you're compiling against it in a separate compilation, you will be able to correctly invoke this method. In order to be able to correctly invoke this method, you need to make sure that when you compiled the method and now when you're compiling a call to it, you think that it has the same signature. Mm-hmm. The most reliable way to achieve this is by doing the transformation in the denotation transformer, because then it will run in the same way regardless whether you're compiling it now or whether you loaded it from the class path.
Okay.
So denote transformers rarely change the underlying denotations. Most denote transformers, which are actually very simple and they want to think in terms of symbols. In order to simplify this, we have the sim transformer, which is a helper trait which allows you to transform on symbols. So for example, what we had now, so we have a phase normalized flag, which gets rid of private this and protected this. What it does, it takes a symbol, it copies a denotation of this, it takes a sim denotations and copy denotation of this sim denotation. We also have identity denote transformers. That's the case where you're doing this nasty stuff by changing the denotations by hand inside a tree, inside the actual phase. In order to indicate it, we have a helpful trait which implements for you the transform, which is identity, and helps us understand that this phase may be doing something nasty. Okay.
What did you cover so far, Dmitry?
So I covered the link between named types and denotations. I didn't go into what kind of denotations exist, so I didn't cover joint denotations. I didn't cover unique graph denotations.
Okay.
I didn't really cover multi-denotations. I explained why we do need signatures. I explained how denotations reload each other. How that we compute them currently, that we compute them lazily, that they transform through info transformers. I didn't introduce the sim denotations yet. Okay. So I didn't introduce this hierarchy.
Okay.
I introduced those links.
Okay.
So
and did you go inside the classes? Probably not. Just what's available on them and things like that.
I went quickly through the fact that they remember the period, that they make a linked list between each other, but I didn't cover the API.
Okay.
I think you'd be the right person to do it if you're willing.
I'll do that, yeah.
I also think that you'll be the best person to explain what the unique graph denotation is and joint graph denotation is, because they have zero documentation.
Oh, yeah. Okay, cool.
Okay, so...
Okay. Let me just get up there. Right. Oh, let's see what I can do here.
Okay. There's also VS Code there in the background, but it doesn't find all usages, so we started using IntelliJ instead.
Okay. Find all references, you mean?
Yeah, it doesn't find all of them.
Ah, okay.
Only in open files somehow.
Sorry.
Only in open files.
Only, yeah, that's, I noted that, yeah.
That's probably broke something. I'm trying to fix it now.
Uh-huh. Okay. I just have to get used to the keyboard. Okay, can you, what's the best screen size for people? It's fine. Okay,
Yeah,
let's-
okay.
I guess for people watching, it's fine. I think with that.
Okay, I just want to split my screen. Split edit. Okay. Okay, and get rid of Explorer. Okay, now we see a whole lot. Good. So,
We're in the matrix now.
we're in the matrix now. Go into Zen mode. Okay, that's fine. Okay, cool. So, let me just start with the denotations. So Dmitry already has explained to you essentially that name types they just have a name and prefix as fields, but then essentially they contain a denotation which is dependent on the current period, right? Okay.
Right.
And denotations are essentially packages that may contain a symbol and contain a type. So essentially they tell you what essentially you're referring to at this point. And if I compare a symbol with a denotation, then essentially a symbol is a definition that the compiler sees in your source file at some point in time. So it sees a given definition, and as long as the definition doesn't change it, it's the same symbol. The compiler will essentially keep the symbol. Once you change the definition or an enclosing definition by recompiling, for instance, you get new symbols. But a symbol is essentially something that stays the same, or that has essentially is an anchor point that's the same thing during a whole compilation run. And the next run you might get the same symbols if nothing has changed and you still keep the things loaded, or you might get new ones. Whereas denotations, they change much more often. They can change after every phase, and that's done with these denotation transformers that Dmitry introduced. Okay, cool. So here's sort of the basic diagram that we say, good, so types, they have denotations, and the denotations, some of the denotations can refer to a single symbol, and some of them can be overloaded, so that would be a multi-denotation. And so, okay, let's maybe go to this hierarchy here. So a denotation, what can it be? It can be a single denotation, which means it refers essentially to a single thing. Or it can be a multi-denotation, which means that it refers to several members that are overloaded. So the name doesn't uniquely identify the entity that it refers to. So multi-denotations are sort of things that overloading resolution has to get rid of. And once I've done overloading resolution, I have single denotations. And the single denotations now, they essentially fall into these subcategories. There's one more, which I don't know whether that got lost. Sorry?
Joint ref denotation.
Joint ref denotation, yeah. So that's here. Joint ref denotation. So a sim denotation is something that I store in a symbol. So I said a symbol is something that essentially is a definition, corresponds to a definition in the source trees. So almost everything that I need to know in a symbol is itself in a denotation, because it might change between phase to phase. Done with a symbol transformer or any sort of transformers can essentially affect that. So for instance, if you have a symbol that is, let's say, a nested method, then polymorphic nested method, then its type might change at a number of places. For instance, in erasure, I get rid of the type parameters. Its owner will change in lambda lift, because after lambda lift everything is flat, and its flags might also change between phase and phase. So a lot of the info that I in the Scala C compiler were in symbols, and in the conventional compiler are in symbols, now are in denotations, and these denotations essentially they change wholesale. So essentially the function from symbol to denotation is also indexed by period, by phase, so it might change in the next phase. Okay, so sim denotation then is a denotation of a single symbol, and it has a further specialization called a class denotation, which is the denotation of a class symbol, and there are certain fields that are only relevant for class denotations. Now, it could be that, let's say I have, let me just create a new file here for scratch. So let's say I have a class A and A of t, and I have an object, and a def f of type t up here, and I have an object B extends A of int, and here I ask for f. Okay, so what's the denotation of f? You could say, well, it's the, I look up the symbol, that's this f up here, obviously, and its info, the type of the symbol is t, but of course t is not relevant down in B, it's not bound or anything. So the denotation is a unique ref denotation, where essentially the symbol is f, and the info is int in this case, because essentially that's the instantiated info, right? So unique ref denotations means it's not a sim denotation in the sense that it's the type has changed from the original type of the symbol, but the symbol is still a single symbol, so I'm referring to a single definition here. Now I could go further and have, let's say, a class B of t, and there I also have a def f of type t, something like that, and so it's C, so it's trait. Let's make them traits up here, or let's make this a trait t, or trait d of t. Okay, so I'm improvising here, and the object B extends A with B, with D, with the trait. So now when I look up the f, it actually will give me a joint ref denotation because it found two references. So in this new case, f will be a joint ref denotation, and the symbol will be probably the f in D, I imagine, and the info is still int. So let's do something more interesting.
You want to write d of int in the extend case?
Here int.
No,
So
in the
extends A of n with D of n.
Okay, let's make this A of t, and let's make this D of t, something like that. So if we do that, then in the first case where we just extended A, the info.
Your extends clause refers to t, which is undefined.
Oh, sorry, that should be int. Yeah. Good point. Yeah, int in here.
And then the return method, the return info should be expert type.
Which one?
The f.
Yeah, expert type. Okay, good. Yeah. So in the first case where it's essentially I don't have this extension, I get a unique reference denotation. The symbol is the f in A. There was no other, and the info is an expression type of A of int. So something like that. Internally, that was an expression type. So, but yeah, I use external syntax here. So, okay. And in the second case now, we have something more interesting where we have an f, and the question is, what is the meaning of f in B? And the answer here is, well, we have extended this by these two things here. So I look it up and I find that the f, that the info here will be A of int and B of int, D of int. because well, I look it up in both parents, and it gets a type, and I conjoin the types, and I will still have a tiebreaker of what the symbol is. In this case, it will, I think, pick the symbol in D, but the denotation will say it's a joint ref denotation, so the symbol is just essentially one of a number of representatives that I have here, and the actual type is this thing here. Okay.
Excuse me, I don't
Yeah.
understand the n type here.
And which type?
Why do we have an n type here?
N.
And
The intersection.
Oh, the and. It's because it looks it up in both parents and gets a denotation, and it joins the denotations. And if you find a denotation in this parent and in that parent, then it will always essentially logically join them.
One other note, because they don't have arguments, they are not considered as overwrites by Dotty.
Yeah.
Or overloads.
Yeah.
They are the same method.
Yeah. So you could say a completely equivalent case was when, let's say, we have a val x, which is a of int and d of int, so an and type. Oh, this should have been. Okay, and we do x dot f, then we would get the same type. So we have an and type here. So to look up f in an and type, I look it up basically in both parts, and I join the things I find. That's needed because and is commutative. So I can't play favorites and pick one or the other. Right? So yeah, so it has to be something that doesn't depend on the order of A and D here. Okay.
So,
Yes.
so in this case, you have abstract methods. If the one or the other of the methods were concrete, what would happen?
Good point. It would affect essentially this tiebreaker symbol in joint ref denotation, which, but the type would still be the same. So the type is still, it doesn't matter. So the type is always the conjunction of the two types that I find.
Okay, but then somewhere there would be a check that the type of the implementation is a subtype of both the types?
Yes, when you define things. Let's see. In this case here, that class here would actually not be legal. So let's make it an abstract class, and we're good. Because the check that's missing here is to say, well, in that class, what is the definition of f? So we had a reference to f, and there I conjoined the things, right? So what is the definition of f? And it would say, well, the definition of f is the one I get from linearization order. That would be the D one, right?
Right.
And then there's a check that says, well, that the type of the definition of f must conform to essentially this conjunction of all the inherited things.
Okay.
And in this case, it isn't, because D is not a subtype of A and D. So there will be an error, and it will say, well, you need to essentially give an overriding definition of f in class B, which has a type which is at least as good as A of t and D of t.
Right. Okay.
So that's also why this thing here works. So essentially why the tiebreaker doesn't really matter, because essentially that thing will be in the end the symbol that we call in JVM bytecode. But the type will in each case be cast to this type that we know here at the latest by erasure.
Right.
And because of this global condition, we know that the actual implementation method must at least be as good as this type. So it doesn't really matter which of the two supertype methods we call here. So that's essentially the. Oops. Yeah, I have to remap mine.
And just if f were implemented in trait D.
Yes. In here. So
with the current type, you would get an error when you extend A and D because the implementation has type D of T, but not A of T.
That's right. That's correct. Yeah.
Okay.
And that's also a very good illustration why you don't want to go through the symbol. Because if you ask for a symbol like x.f, The
Yeah.
info of x.f is different from the info with symbol of x.f.
Yeah. Right.
Right.
So the symbol can't express alone can't express these subtleties, right? In the types that I have to conjoin
Right.
them or adapt in subtypes or all these things.
Right. And one other question about the difference between a unique graph denotation and a joint graph denotation. Is it just a difference in the implementation, or from the outside, do they somehow behave differently? So, I mean, you've shown that they have a symbol and an info.
I don't think they do actually.
You get a different info, but from a user's point of view,
No,
do
it
you
doesn't.
care about the difference between the two?
It doesn't really matter. There's one thing that I'm currently looking at, which is I think that's actually the only place I need it. It's not in yet. It's a pull request that's causing me a lot of grief because of a deeply hidden problem in Bootstrap, but whatever. So there was a thing to say, just to illustrate, if you have a super call, super.f, then the problem is in a super call, the meaning of this f should not be that, because that's not what it is. That's not what I get from the super, right? So this dot f has this meaning, but the super of f shouldn't. The super of f needs to select a base class. And what happens there is in the new pull request to say, well, if it's a joint ref denotation, then that means there was a conflict. Then essentially go and look at the symbol that it selected and recompute the type of that symbol relative to where you are with an scene from, and that's your new type. I believe that's the only thing where I actually make a difference as a consumer for joint ref and unique ref. Otherwise, nobody cares.
So the entire Dotty code base only has mentions of unique ref denotations when it's constructed in a new. There are 2 mentions in the entire code base
Of joint ref denotations? Or?
of unique ref denotation.
From joint ref there's one.
Oh yeah.
Yes.
So
So
they're not that many.
they are transparent.
Okay.
Okay. And
Okay.
do they have a common superclass, or
Yes,
or are they
it's in this
used
diagram.
the same way as sim denotation?
No, it's missing in the diagram. It's non-sim single denotation.
Non-sim single denotation. Okay, there's one in there as well, but that's sort of, yeah. So
Okay.
nonsense, but I don't think we need that. Yeah.
Okay.
Okay. Cool. Yeah. So maybe we just go in denotations and see what's there, like we did for types. So again, here's sort of an explanation of the notions that you have here, but we went through them already. So this EQ, that's our essentially thing, multiversal equality, that we say we can't accidentally compare denotations with anything else. That's just to keep the compiler itself safe, that we don't do stupid things. Okay, so what does a denotation have? So a denotation has a symbol, but it can be no symbol. So no symbol says this denotation doesn't refer to anything, but as long as it makes sense that these things came from a symbol, we will keep a symbol in there. And the denotation has an info, but only for non-overloaded denotations. For an overloaded denotation, so if it's overloaded, it doesn't have an info. It has an info or completed. Did we cover laziness yet?
I covered it a bit.
Okay, yeah. So, so I wonder whether we should do maybe we should do some denotations first, because they're more concrete, and then go to denotations. Okay, so let me take you out of context and swap and do sim denotations first, because I think that's more concrete. So sim denotation is what's in a symbol, and the main things that are there are, let's just go down to the class sim denotations. Okay, so a sim denotation obviously always has a symbol. That's the symbol that essentially owns it. It has an owner, where that's this one here. So that generally every annotation has an owner, except for no denotation. So no denotation is, as you know, you recognize the general patterns in the compiler. This is essentially a no something sentinel for everything. So no denotations as well. There is really no denotation, and then I don't have an owner. It has flags. We covered flags already, didn't we? A little bit, or should we go into that?
I actually think we didn't cover flags at all.
Oh, we didn't cover flags at all. So that's something to do. So flags are a bunch of things, from things like private, protected, lazy. So all the modifiers that you would see in a program, but also a lot of compiler internal things. So that's a flag set. So it's the flags. That's represented as a long 64-bit int, and the flags can be set in a symbol, so that's essentially a non-functional aspect there. So I can override the flags either with global operation flags equals, so that will install a new flags, or set flag, reset flag, which just essentially sets or resets a single flag. I have okay. The next important operation is, so that asks whether a symbol has a certain flag set, and the so there's we get to initialization. So for the moment we'll just skip over the implementations here. And there's another operation which is useful, which is but not. So you can ask, well, does this symbol have a flag set? So it means if there are several flags, it means has it one of the flags in the flag set, but at the same time has it none of the flags in the sort of excluded things. So sometimes you see an is flags, but not the other flags. So okay, so that's a slightly shorter and more efficient way to essentially have multiple tests in here. And then there's a thing called a flag. We have to. Okay, let me skip over that because we're in sim denotations. So essentially, a flag set is an or disjunctive. If you ask for a flag set, you say any of the flags in the flag set are true. And the flag conjunction is an and. So that's essentially also represented as a long, but it has a different meaning now. Essentially, the symbol is a flag conjunction only if every flag in the flag conjunction is set in the symbol. Okay, so that's flags. Then I guess the most important one is info. So that's the type of a symbol, and that has essentially is the core of also the completion. Because of all the cycles we have in symbols, we can't typically set the type of a symbol immediately when we create the symbol, or often we cannot. So what we do is we have a type called lazy type. I think that we've seen once when we saw the types. So that's a subclass of types where we say the type, that's a type that essentially you have to complete further to get to the real type. And so if you take the info of a symbol, you first look at the variable myInfo. If it has a lazy type, then you complete the symbol. So completing is essentially a code that's stored in the lazy type in here that essentially will know how to essentially set all the attributes of a symbol, all the attributes that are not constant. So in a symbol, that's essentially the flags, the info, and the private within. So that's those are these completers. Typically when I look at any of the fields of a symbol that essentially need to be completed, then it's lazy that essentially they would trigger a completion from the symbol. And the completion could be several things. It could be that I go back to the namer and typer to say analyze the source tree. So that gives essentially the full definition of the symbol. So for instance, I have a val or a def that doesn't have a declared return type, then it would get a completer to say, well, to give me the full type of this val or def, essentially type check the right-hand side, and once you're done, that's the type. Or it could mean read a class file, either a tasty file from Dotty or a Java class file or a Scala class file, or read a part of the class file to actually fill in the missing information. So that's a core piece of the front end, and it's one of the most subtle ones. So whenever you have a cyclic reference error, we get to that, yeah. So we get to cyclic references in 5 lines. So sometimes, very rarely, I'm actually interested to also see a lazy type. So that means for that I have a thing called info or completer. So info always gives me a real type. And sometimes I might want to look at the symbol and says, is it completed or not? It's dangerous because that sort of gives you sort of something that feels like a race condition. So you look at the state of the current symbol, which essentially might change at any instance that somebody demands the type of the symbol. So for that reason, it's discouraged, and you should just, if you can, should just use info. And unforced info is essentially the analog of info, which just says, well, if it's a lazy type, then you won't get an info, and otherwise you will get an option of your info. Okay, so we saw that in the info we said, well, if it's a lazy type, we do run complete from. So that's the complete from method that you see here. Oops, that went fast. Yeah. Okay. What it does is it will essentially the completer, that's my lazy type. The lazy type has a completion method, which depends, essentially analyze, type check some piece of the source, read a class file. So the options that I've given you, they're basically all implemented by this completion methods here. And so we run the completer, and now it could well be that running the completer will recurse back to yourself and essentially force your own symbol to be completed again. So because you have a cycle, and there's a cycle detection here, which is this done with this touched flag. So you say, well, essentially you set flags to touched, that you have touched this thing, and if the flag is touched, then you throw a cyclic reference. So cyclic references, I guess, is not an uncommon occurrence when you work with the compiler. That's where they come from. Right. So if you have a cyclic reference, then there's a useful thing called essentially it will print to a certain printer. Have we covered printers yet? Probably not, so we should do that. Oops, I just have to get used to the keyword here again. Okay, so printers are really useful. So a bunch of very useful stuff is not printed to the console because it would completely swamp your output, but essentially it's all printed using a printer. So there's a thing called in tools config printers, and by default they're all no printer. That means they will print nothing, except there's a default printer which nobody uses. But you can then, if you know what you're looking for, you can then essentially selectively enable a printer like this. And that means that everything that prints to that printer, like in this case typer.printer, will essentially, you will see that on the console. So in this case we had the completions printer. That's this thing here. So let's say you get a cyclic reference error and you want to find out where it came from. So one thing would be good to see a stack trace where it came from. So that's here, cyclic errors. Make cyclic errors into a new printer. That means every time you get a cyclic reference, you see the full stack trace. Your program will continue if it recovers from the exception, as they usually do, because they just convert it into an error. But you see the stack trace that caused it. And the other thing is completions. So completions is also nice because it gives you essentially a full trace what gets completed. So we can have a look at what happens here. So you see that essentially it's sort of an indented map where it tells you essentially when it enters a completion, when it exits a completion, and then you see what got completed. So you see exactly essentially how you got to the cyclic reference here. That's just for debugging, but by default all these things are off, so you won't see anything that's printed except when you turn it on. Okay, and then what does a completion do finally? Well, it reads a class file or analyzes a tree, but in the end it will call info underscore equals. So that's the setter for the info, and that hopefully will set the info to a normal type, not a lazy type. So the next time I run info, I won't fall into this case, and I just return the variable unchanged, and that means I won't get into the completion. And that also means that this flag will not trigger, because I mean the flag here, you see it stays set. So if somebody tries to complete this thing after it's completed, that would give you a cyclic reference as well. But nobody does, because everybody checks the info here. Okay.
And just a question about the cyclic references. So those are something that is intended to happen, right? And if somebody compiles an invalid program with cycles
yes,
in the references?
Yes, there are cases like where this happens. Yeah, there's an effort made to convert this in some cases to a more recognizable error message. So one thing where it happens is, for instance, a recursive method without a result type.
Okay.
Because you need the info to get the info. You analyze the right hand side. The right hand side sees the recursive call and needs the info, and that's when you hit it. It can also happen with an overloaded method that doesn't have a result type. Same scenario. It looks at all the overloaded variants and tries to pick a best one, and for that it needs the types. It can happen in a number of other scenarios as well. Mm-hmm. So it's basically, if you get it, then yeah, it could be either. It manifests itself as a program error. If it's none of the specific ones, it will just say cyclic reference involving symbol, and it will be the symbol of this denotation that it prints.
Mm-hmm.
Yeah. Okay.
Okay.
So. So the next thing is private within. So that's essentially, there are these public or private things. Yeah, here we have one, protected core. So private within would be the core object or class that encloses the current denotation. So that it says the symbol is private up to this enclosing thing. So that's stored here. And you see, to get the private within, you do an ensure completed and then my private within, because private within gets set alongside with symbols. So there's certain attributes that always call ensure completed, because you need to have the full info, because the full info the computation of the full info will set it. There's annotations, and again you can override them later. And for annotations, so there's a basic one which is essentially gives you a list of annotation. An annotation is a data structure that represents a annotation in the language, as you would expect. And you can also ask whether it has an annotation that refers to a certain class. You can transform all annotations with a mapper. You can filter them. So there are a bunch of methods that essentially look at annotations, add annotations, remove annotation, update, and so on. Okay, so but I mean, you typically look them up when you have to work with them and see whether there's something that approximates what you need to do with them. Okay, then since we were talking about completion, we have here some status flags. Is completed. It says, well, it's a symbol completed, and that you see that means that the info is no longer a lazy type. So then it's considered completings. is completing means the flags are touched and it's not completed. That again is sort of a racy thing to use with care. The completer, that's a lazy type, so then there you must know that it's not yet completed because it's a cast to a lazy type, so that will fail if it's completed. And ensure completed, what we've seen before. So ensure completed just calls info and that will force the rest. Okay. Right. Then we have another one. So there are some operations that are called unforced, and all these operations have to be used with a lot of care and only in emergency situations because they are compilation dependent. So if you call the decals are essentially the decal declarations that are in a class, defined in a class, then typically decals will essentially go through the info, and that means the symbol will be completed, and then you will get what's in there. Unforced decal says, give me whatever is in there without bothering completion, and that, of course, very much what you will see will very much depend on compilation order, whether somebody has happened to complete the symbol yet or not. So that is very dangerous, and therefore there's a long comment, and it says careful, and you probably shouldn't use it unless. So typically where it's used are situations where if you don't use unforced decals, you run into a cyclic reference error and there's nothing you can do about it. And then you have to sort of convince yourself that it's still safe to do this unforced decals in this particular instance. So first thing, you must have run into a cyclic reference error to even consider using it, and then you should really think hard on a case-by-case basis why you think it's safe to use it and why it's not why order dependencies wouldn't matter here. I don't know whether we have a thing. Let's see. Is there a find references?
Find something in open files.
Yeah, but we got some of them. Let's, for instance, look at that one here. So where was that? Now I have to go back. Oops. Half of my keys don't work. Okay. Oh, here we are. Okay. So that is what is that? Trace invalid. Oh, yeah. So you see, so here is explain why a symbol is invalid used for debugging only. So then, of course, it's okay. So if you do something for debugging, then you don't want to force things while you debug, because that would essentially mess up your things. So you want to do unforced decals to say, well, if I don't see everything, then so be it. It's a best effort anyway. So what do we have here? Same thing. That's the thing here. Current package decals. Yeah, that's a. Yeah, type params from decals. Yeah, you see, every time it's used, there's a fat comment up here to sort of explain why it's safe to do so. And I think if I would see a pull request where this is without such a fat comment, then that wouldn't go in. Okay, cool. So let's go back to the symbols. Right, where were we? Yeah, that were the annotations. Unforced decals. Okay. Okay. Right. Then we have a couple of operations on names. Let me just do a simple thing. Yeah. Okay. So we haven't covered names yet, have we? No. Name kinds and things like that. Ouch.
You said that names are type names and trend names. That's what.
Yeah. One thing needs to. Now they're actually much more. They're sort of semantic names. They have a structure. So an expanded name is if you see, for instance, if you have a class list of T, then the compiler actually maps that into, let's suppose we're in package Scala, Scala dollar list dollar dollar T. So that would be essentially a type member that is publicly visible. And because it's publicly visible, I have to mangle it that it won't accidentally conflict with other things. So these are called expanded names, and that I can find out what the expanded name of a symbol should be if it's yeah. So there we say, well, if the name is already an expanded name, then give me back that, and otherwise, essentially compute a thing on the names. There's an original name, which is essentially the name with which the symbol was created. That's useful in databases when you got mangled names and it says, well, what was the original name? And then there are various full names, and so the full name is essentially just something like Scala dot collection dot mutable dot list. So that's a full name, periods in there, and if we after flatten, it would look like what would it look? You have names with dollars, so these are flat names. So you have various forms to essentially create these names. Okay, cool. So let's have a look at. So then we have a bunch of tests, but now I wonder whether I should do everything or quickly skip. I'm not sure whether there's anything. So there's a lot of things in here. No, I think we skip the tests. They are probably not so super important, though. It's sort of all the different things you might want to look for. Okay. Yeah.
So, may be interested in is nullable class.
Is nullable? Where was that?
Is nullable class.
Yeah. Okay. Yeah. So that's. I'm not even sure we use that a lot, do we?
Oh, but that's the intended
right.
place where the proper implementation should go.
That's right. Yeah. So that's a class that essentially. There the test says, well, is this a class that would be a supertype of null? So here you say, okay, it's a class. It's not a valid class, so because they don't have a null. It's not a modular class, and it's not the nothing class, which is essentially nothing is under null, so null is not compatible. And then there's something about phantom types. It's not a phantom terminal class, which is then nothing or any of a phantom type. They are also not compatible with null. So this is nullable class, but it's probably not used a lot. Derives from is important. So that's essentially the general test whether the current symbol is a subclass of the base symbol. So here, because we are in general symbols, that's false, but it's overridden in class symbols. Is accessible from is essentially a fairly involved operation which says, well, given a prefix type, a site from which I ask if that's a symbol, so and we have a thing of type pre, so let's say x of type pre, and then .f. Then it asks whether f is accessible like that, and there's a flag which says, well, is that thing really a super access? So does it go through super in this type or not? And so there's essentially it's all the access rules in Java and Scala which are a bit subtle, in particular what concerns protected access. So I won't go into the details, but you might have already seen that protected access in Java is actually very, very subtle when something is accessible, protected or not, and that's where it's implemented here. Okay. Then there was this question, well, that you had, Andre, what if one symbol is is concrete and the other isn't? So there's a test for that that's called is as concrete. Does a method have default parameters? Okay, cool. So I think the tests are fairly self-explanatory. The next here's the next thing is essentially the things about modules and module classes. So a module in the compiler is basically, in the source language, it would be called an object. So object C, something like that, right? Or object M for a module. So what the compiler does with that is essentially a lazy val. So essentially there's a class $, so that's a module class name, so that's an internal name which contains a definition of this object, and then a lazy val $, equals new $, something like that. And then here in the $, there would be essentially a self-reference to say, well, I know that I am actually that would be m.type. I am the m. There's only one object of this module, so I express that in the self-type of the thing. So that's how Dotty can essentially compile away objects, and that way objects are no longer a primitive concept. By and large, there's some special cases where we look out for these things, but not very many, and that's the translation. So the relationship between the m and the $, that's basically in those two things. So the module class, if m is a module, then its module class is this $, class, and if I'm if the symbol is the $, class, then the source module is bm, is the thing. So you see the way it does it is essentially to go from the module to the module class. It just looks into the type. So we have to be careful. The type might be lazy, and then it's actually stored in there. So there's some essentially exceptions to deal with these situations, but by and large, so the normal case is to just say the symbol of the type. That's the module class, and the source module again, it looks into the self type of the thing and finds its symbol. So that will give you the source module. So that's the two things that we have here.
Okay. So these are essentially all inverses.
They are inverses, yes. Yeah. Yeah. Okay. Then we have the field accessed by this getter or setter. So that is essentially when we much later in the pipeline we actually create actual fields for well, if something is created like this valix in a class, and it's not, so the only difference is, so then actually what Dotty makes from this is it says it's a defix of this type, and it marks it as an accessor. So essentially it marks it as, so that's another flag that we have, accessor defx type. So that's what we get, and because the point is that that way these things can override other things and so on. So much later we actually create fields for these things. So then we create essentially another field that's after erasure, and then once we have fields, then we can essentially get from then we can get to the field. Otherwise we get to the setter. Okay, so sorry, I have to. So if I do var yt, then it gets to the same thing. It gets essentially two things. Access at defx, so it gets that. Oops. No. I have to get used to the keyboard. No, still not. Is it V? Ah, no. I don't know. Is it command?
So,
no, it's not command.
It's control, but you copied it previous time, a long time ago.
Control C.
Yeah, control C. Control V.
Okay. No?
Is
Control V
I
doesn't work.
somehow better than IntelliJ, or are
No.
you just testing?
No, it's my, it's, I don't know what it is. It's my keyboard, which I probably should have used. It's my Mac keyboard that somehow doesn't work with,
Okay.
sorry? No.
Are you pressing control or command?
Alt and
Yeah, so press Control.
Control.
Yeah.
Cool. Got it. Okay. Okay, so it gets into these two. It gets a setter and a getter. And they have all the accessor flags, and essentially to get back to either the field or the getter, I have this access field or getter. Okay, so the next group of symbols have to do here with owners. So every symbol has an owner that goes up right. Essentially, it's always the enclosing symbol and goes up all the way to root, which is essentially the symbol that contains everything. And root itself, the owner is no symbol, and the owner of no symbol is not defined. So that's the dreaded no symbol doesn't have owner things that you have seen. And here in Dotty, they would probably say no denotation doesn't have owner. So to get all the owners, it's mostly used for debugging to print this. There's an owners iterator that essentially goes through the owners up to root. Then there are some things that skip weak owner. So weak owner is if you say, for instance, if you have a def f, and then I have a val x equals, and then they do a val y equals 3 to 33. Okay, something like that. So there you could say, okay, what's the owner of the y? And you could say, well, it should be the x because it owns it, and indeed it is the x. But the x is then called a weak owner because it really matters, in particular later, that it's the f. The f is the anchor point of the method. So, for instance, if I would reformat this code or then maybe the y gets pulled out here, but it's still contained in the f. Okay, that's the skip weak owner. Then would essentially go from the y directly to the f and skip the x. Okay, enclosing class gives you the class containing this declaration, and there's something very subtle with Java static, which I will skip now. Okay, enclosing method gives you the method enclosing this declaration. Top level class is useful. That gives you essentially the class up that is itself owned by a package. So that's the class that's not contained in another class, and that contains the current symbol. So that's the current class that's furthermost out class. Okay. And then we have another one important set of methods, companion modules and companion class. So we have seen here module class and source module. Companion module and companion class would be if I define next to the object M also a class M. So now the companion class of either this thing or that thing is this class, and the companion object of the class is the object here. So essentially the two go together, and the way it's done is to make this stable is that essentially we put magic methods with the right type in the scope of these things that point to the other. So we essentially to go from to find the companion class of an object, we say, okay, look for a denotation named companion class method, which is a synthetic name that is compiler reserved, and if that exists, then the class will be the class symbol of the result type, and the companion method module is the same thing. Okay, there's another one that so this is the much more difficult method. So that does it manually to just look at it, look at all the things, which is difficult. But you don't need to call that, because essentially when we form these scopes the first time, we will, using this method, essentially look set companion class and companion module. So afterwards, it's a simple lookup. Okay, linked class is like companion class, but it goes from the module class to the class and back. So $m and M, the class $m and the class M, they are two linked classes. Okay. Okay, let's see, what do we do? Yeah, so the next bunch of methods has to do with overriding. And and the core method here is probably this one here, which says matching member. So so we have a call like some symbol denotation dot matching member and then a prefix type. So that says we look inside all the members of the prefix type of this prefix here and find the one whose type matches the current symbol. So we say, okay, look at all the non-private members because otherwise they couldn't match. If it's a type, then there can be only one, and that's the one that you found. If it's a term, then you have to disambiguate because terms might always be overloaded. So there might always be several things. So there's a thing called matching denotation, which you give essentially the member info of the current thing. So you say, well, our current info relative to the prefix, what's its type? So that's the site.member info symbol. That says, well, because the type of the symbol might not be the same type as what it looks like in prefix. So that's this member thing. And that's the thing we give to matching denotation, and that gives us matching member. Matching decal is basically the same thing. So the difference between decal and member is always that decal is the things defined in your own class, and members is the thing that you have defined or inherited. So members is always the thing inherited. Things always matter for members and never matter for decal. So that's the core methods, and then you have things like overridden symbol. So that's that you say, okay, I'm in a symbol, and I said, well, what symbol does it overrides in this class, in class? So there you say, okay, I want to essentially just find a matching decal in this class of my own symbol. I can say all overridden symbols, so that's essentially all the symbols that are overridden in any base class. Extended overridden symbols, that's even more, because the self-type of a class might actually mention things that are not direct superclasses of a class. Okay, and then the other one is called overriding symbol. So where we say it's the opposite, right? So the in class is now supposed to be a subclass, and we say, do we have a symbol that overrides the current symbol? Okay, that's the most important one, I think. Right. Okay. Yeah. And then primary constructor is also very useful. That's if you are in a class, then it gives you the primary constructor of the class. So that's essentially the thing that is the that represents the arguments of the class. So that's represented as another symbol called the constructor. And there can be several, because you can also write secondary constructors with this. So the primary constructor is the one that essentially corresponds to the class arguments and the class body. Okay. So then we have a bunch of things that are also quite commonly used, type related. So the first ones is, if it's a class symbol, then it's type parameters. So the type parameters of a class, that's very used all over the place. The next one is the this type. So what we would write in source c.this. So the this in this class, that's also used all over the place. So type params and this types. Then we have type ref. So that's essentially if it's so for so that would be the type C, that essentially that corresponds to the class, and it's the same thing if this has a parameter. Let's call it like this. It's a type with exactly the same. No, sorry, it's just the class ref. It's not the type. So the type ref is just essentially a reference to this class. Okay. a term ref, that's method. Okay, so that's if you have a field or method, then and you want to form the type that refers directly to this method, that's term ref. A val ref.
What?
Yeah.
Why is the passed to these type refs and term refs?
Sorry, I didn't catch the question. Why is there?
Why is this passed to the type ref and the term ref?
Oh, here. Right. Okay.
The last argument.
Yeah. Okay. Okay. Yeah. So let me. That's the. Okay. We'll get to it in a second. I just finished this. Okay. So let's just go to it. What it is. So yeah, now I have to pick the right one. It's one with 3 things. It's this one here. So it creates a type ref with a given prefix, that was this type of the owner. The name, that's the name of the current thing. And then it gives you the denotation as well. So
okay.
So
So
that
that's
means
just a optimization to not have to recompute it?
no, actually, it's necessary. It avoids some cyclic reference errors that would appear otherwise.
Ah,
Yeah.
okay.
So, but that's why we have this this particular thing that because at this point we know the denotation, so we can avoid recomputing it,
Right.
and the recomputation at some points might have led to cyclic reference errors.
And for
Okay.
term refs, it's also necessary because the thing can be overloaded. So
Right.
and the name doesn't know the signature.
That's right. That's the other thing. So for the term ref, it's very necessary because if we have to essentially add the denotation here. Actually, for a term ref, in most cases what one does is one doesn't use term ref but term ref with sig. Have we talked about signatures yet? Maybe not.
Well,
No.
Sort of, but Dmitry said you'd discuss it later.
Okay. Okay. Yeah. Right. So a signature is an object which essentially consists of a bunch of type names identifying an alternative of an overloaded collection typically. So essentially it says that it's the type of every parameter and the result type after erasure. So I erase them all, and I just pick essentially the class after erasure and its name. So that's the signature. It's very close to a JVM signature. It's just essentially I don't have symbols like brackets and semicolons and whatnot, because it's all used internally. They're just essentially a list of parameter names and a result type name. So that's what a signature is, and it's used to disambiguate overloaded symbols. So if I want to refer to an alternative of an overloaded symbol, then typically I would use that. I would say, okay, it's a term ref with signature and denotation, where I pass the signature and the denotation in here. So the signature sort of fixes it and say, well, if you recompute this thing later, you will always fall back to something that has the same signature as the previous one. That means that you will not get another ambiguity or flip to another overloaded variant or things like that. So signatures are important because essentially they make, essentially they let us keep this abstraction of term refs as just names and prefixes, even in the presence of overloaded symbols, because in a sense the signature we can treat as part of the name. Maybe actually we should, and I think that's actually a refactoring which we could still do, that we get rid of signatures as they are and make them part of the names. I'm not sure. Because we have now semantic names that essentially we encode all sorts of things in the name by a structure, and why not the signature? Yeah, so, but that's sort of the only thing missing, because we did that fairly recently, and signatures have been in for a long time, since the beginning, so they were not integrated in the scheme yet. Okay, right. So the next thing, well, there's a variance thing, which is essentially it's a variant of a type parameter. So there are two flags, covariant, contravariant. But in most of the other compiler where we don't look at flags, we treat them as ints. So covariant is 1, contravariant is -1, and non-variant is 0. Okay, and then there's a toString, which is generally toString is only used for debugging. Whenever we present something to the user, we use a printer, and that goes through a method called show. Okay, so that was that, and the last one, or almost the last one, I think, right, is this one here, copy sim denotation. So I think we've seen a usage of that before in the info transformer. So that says essentially, given a sim denotation, give me a copy, and I can override certain things. So that essentially takes everything that I need. For sim denotation, I need a symbol, an owner, a name, flag set. It's called init flags because I can change the flags afterwards. An info, a private within, so up to what it's visible, and annotations, and and essentially I would just copy the things here. It's right. Okay. Yeah. Okay. The next thing that's important for right. So that's again, we get back to miniphases. Just can we do a find our references here?
It doesn't find them all.
Yeah, but that's the one I needed. That's fine. Okay, so yeah. Okay, yeah. So that will be in denotations. But the point is when we might in a mini phase create new symbols, and we have to then link them, essentially install them in the scopes of their owners, and these sort of things. So typically, again, we should never do this just with enter in the scope, because that's again a race condition. So suddenly these symbols pop up, and we don't know when they're there and when they're not there. So what we typically do is that we say, okay, after the current phase, which is this denotation transformer, we want to see the symbol. So that's this install after, which essentially will make a copy of the but it will ensure that the parent has a copy, so that the parent is new, and we'll get a new scope, and that scope will essentially contain this symbol. So that's what this install after was. There's a cousin called entered after, which we have seen, which we're going to see. Not sure where they are. Where's entered after? Well, let's just stay in the flow. Okay. Then the other big part is class denotations, and symbols. Actually, some denotations got so big that we probably should split class denotations and put them into their own set. So a class denotation, classes are essentially subtypes of symbols. So generally, I try to keep sort of. We have a large number of types. And a very small number of symbols, only essentially sim denotation and class denotation. Scala C had a large number of types and a large number of symbols, and that was sort of a combinatorial complexity. So here we try to at least sort of keep one very slow, very small and homogeneous. So the only thing where we deviated from that is class denotations, because class denotations have in particular a lot of caches that take space, and since there are many fewer classes than normal symbols, it makes sense to essentially allocate these caches only in classes. So here you see some of the caches they have. I won't go through the caches because that's sort of implementation detail, but I will sort of more look at what can you do with class symbols. So there's some things that it overrides. So type parameters, for instance. The class parents is the denotations of all parents, the superclass. So all these things are pretty much overwritten, type graph. Okay, but here we have a new one. So that's base classes. Base classes are essentially base classes of this class in linearization order. So if we go back here, the base classes of B, so B dot base classes, what would that be? So that would be, we start with B, then we go D, then we go A, then we go any ref, then we go any. So that's what the base, I mean, it follows the spec of what a linearization is. So linearization starting with the class itself is base classes, and then we have a smaller one which is called base class, a simpler one which is called base class set. So that's just essentially an efficient implementation of the set of all base classes. Because if you have a contains check, whether it's contained in the base classes, then it's more efficient to go through this than through that. So okay, and compute base data does it. Yeah. All right. So derives from, we already had that, to say is a symbol a subclass of the other one. So that's essentially the implementation of this one, and that uses base class set. Is subclass is a variant of derived from. Yeah. Okay. And then we have here now scope handling. So I said already, symbols have classes have scope, and you can get at it by essentially have these decals and or members, which includes inherited members. So to enter something in a scope, I have this enter method. So it's called essentially class.enter member. So that's how I add it, and that's what it does. It optionally gives you the scope of the class, which is, again, it has to do with the fact that we want to avoid cyclic references in some situations. If I don't give the scope, it will just be the current declarations of the class. It will get at them itself. And then there's some variations, like an enter that blows up if the symbol exists already, a replace that essentially demands that the symbol exists, and now I put a new one in, delete, so they all essentially access the scope like that. And then there's another one which we saw in passing in a comment, ensure type params in correct order, so that's sort of a very internal one. That's has to do, I think it only has to do when we read Scala 2 class files, because for a technicality they sometimes are in the wrong order and then we have to reorder them, but okay.
So these are all destructive updates, right?
They are all destructive, yeah. Enter.
And that's not. Does that ever cause problems, or?
Yeah, that's why when you're in a transformation, you should use entered after. Now let's just see whether we find that.
Okay, yeah.
So all these updates are indeed destructive, and the right way to do it is, instead of updating the existent one, to register an info transformer, which returns the new ones. But handling new symbols is hardish, because you need to transform the owner to change his scope. So doing it entirely correctly is complex. That's why we have a helpful method entered after, which mutably changes the owners.
But
sometimes it does shoot us.
but in the new phase. So basically, it just collaborates to build up the ownership structure after the phase that's entered
Okay.
after. Yeah. So it means
Right.
there's no race, but it sort of, when we build things up, because essentially we have arbitrary complex graph structures here, it's almost impossible to do it without mutation. So
Right.
you have to build up things gradually. But the important one is that at least as you go from phase to phase, so it would be really bad if, let's say, in phase ref checks or whatever, I suddenly enter symbols into the scope of a symbol that was created before, because that means, well,
Right.
that's also it means that since we use our compiler also as the backing compiler of the IDE, in the next millisecond we might be back at typer and with the same symbol, and suddenly it has junk that some later phase got entered, and we will essentially, if it was done like that, just enter it into the existing scope, then it would pollute the thing in the previous phase. So we don't want that. Okay.
Right.
Okay. Cool. Right. So then once we have entered, there's the membership. So that's the next big bunch. So that we say, well, we have to find the members of a class. We saw there's a method called find member in types. Where do I have that? No, I'm still. It doesn't matter. Okay, so there's. Where's my types? It was command.
You have the go method menu. So if you go through go to file.
Oh yeah,
Start-
that's the
start
one.
typing the file name.
That's the one I wanted. Yeah. Okay, that's the one. Okay. So we saw find member here. Sorry, I'm getting control. Okay. I have to get used to the remapping, yeah. Okay, so we saw find member. That was the one. That was the thing that essentially went through all the types and picked the members here. And if that is a type ref, so essentially points to a class, then I look at the denotation in the find member. So that's what we are gonna see now. So here's the find member that we end up with, and essentially that is a fairly subtle thing, the way it works. As you can imagine, finding members is sort of the most common thing, so it should be very efficient. But it's also super complex in a language like Scala, because you might find this thing in all your base classes. It might be everywhere. So what do you do? So essentially what we do here is some very aggressive caching to make this fast. And so there's another thing called a pre-denotation, which is so that's really purely for performance. So essentially what happens is when we do find members, we look at all the base classes and we get a denotation here and denotation there, and then essentially we have to decide to combine them at some point, and we do that lazily. So pre-denotation just says, well, give me everything I have, I put them into a big bag. I don't try to form the joins of two types or any of these things. I just essentially get, that's sort of the set of candidates that I get here. And that's what I get with members named and non-private members named. And essentially there I have a member cache where essentially I look up the name, and if I find it, then that's okay. And if I don't find it, then I have to go through compute. And what you see with compute is it actually goes through the parents of the classes. And for each parent of the class, it does a recursive call to collect, to get the denotation here. And then essentially there's this union thing. which, as you see, essentially is between pre-denotations. So it just forms a new pre-denotation that takes everything that's there. So that's what compute members named does. The caching is absolutely essential here because essentially if you do indirect paths, then if you look at a thing like collections, then class list would have something like 120,000 parents. So the time you reach objects by all the different paths, you could reach objects. So that means that if without the caching, I would visit the object members about 120,000 times. That's the reason why I think ProGuard craps out or used to crap out to things like that. Certain things were ridiculously slow, or it was a VM Android or something like that, because I didn't optimize for that I could reach a base class with many different things.
What has class loading, which is quadratic in number of superclasses?
Yeah, but this is sort of indirect superclasses. So by how many different paths I can inherit object. Yeah. So, but because everything is cached, that's fine, because I hit a parent and I ask the question, well, what are your members? Then the cache will tell me immediately. Yeah. Okay, cool.
But so if you were to call base classes, you only get each class once, right?
That's right. Yeah.
So, but here you can't do that?
I could do that, but that's actually what Scala C does, but that's still too inefficient, because if I am in list, I have only, I think, about 35 base classes, so to visit them all and look them all up is pretty inefficient. Whereas here with caching is, I say, well, maybe I don't have it in list, so let's go up to sequence, then the chance that I found it in sequence is already higher, because that's sort of the common superclass in any. So essentially the way it's done here, the likelihood that I get a cache hit is much better. Okay, right. So that's all there's to say for members. And then the next fundamental operation is base types. So base types are a bit complicated. Let me see, how do we do this? So let me change this example here and put the A in an outer, and then here, let's say I have a val O of type outer, and then I do O.A. Okay, so now I say, well, let's say I have the type B dot this, so I am in B dot this. So what's its parent that is the A class? And the answer would be, well, the full parent is O.A of int. But remember that in Dotty we actually don't keep these type parameters around. They're members. For on that level where the int is just another type member, I would drop it and I would say it's O.A. But not A, but O.A. So the prefix is important. The prefix could be many different things. And that's what base type ref gives us. Essentially, here that's this operation base type ref, which is in types. So it takes a type, it says base type ref of a class, and that gives me essentially the type reference, so including the prefix of that essentially refers to that class. And that again is cached, so I turn it around and I say, okay, compute TP base type ref of this. So look at the class field and say, well, have you already computed a base type ref of a certain type? Because almost all types are hash const. That's something essentially types make good hash keys, and I can have a big cache here that essentially tells me all the base type refs of all the things that I've used here. So that's what this thing does. Okay, what else do we need? Oh yeah, then there's another one, right? Member names. So we've seen single member access. So now we have things that give us set of names here. So that's member names. So what that does is it says, so typically I want to say, well, I want to keep maybe, I want to find out what are all types in a class, or all abstract types in a class, or all type parameters, or all fields, these sort of things. So to do that, of course, I could go through the scope of the class, so that's essentially an iterable, collect it all, and then go through all the base classes and collect it all, but again, it would be super expensive. So again, I cache it, and the way I cache it is I have a name filter. So a name filter is basically a key that contains a predicate that tells me what kind of members I'm interested in, and it's so the parameter is called keep only. So I use keep only as essentially an oracle to keep whether a name should be kept in a set or not. And then again, I cache that one. So I say, well, member names cache of keep only. Okay. So the cache, the apply method of the cache will actually give me compute this thing by itself. Okay, right. Primary constructor we got already. Yeah, and then we have a final one, which is even more special than a class denotation. So it's a package class denotation. So packages are objects, so they have classes, and a package class denotation describes what's in the package. And the subtleties with package classes is that, as you know, there are these package objects, so package object blah. So logically, something in a package object is part of the package, and the package class that controls the package is aware of that. So it will, if it essentially here, if it wants to find a member, it will look in the package object and in the top level classes and objects that are defined as files in the class. So it will look in both, and that's basically it. And then there's a node denotation, which extends sim denotation. It just has essentially defaults for all these things that say it's not applicable. And here we have finally the lazy type. Oh, we haven't seen it yet, so that's here, yeah. So those are the things that essentially lead to completions. So a lazy type essentially has this complete method, which is given the denotation it needs to complete, and it just does its work, doesn't return anything. And certain things you have to sort of know before completion. For instance, you have to know the relationship of source module and module class before completion. So you store these things also as fields in the completer for certain objects. And the definitions as far as they're defined also. So for instance, I might need to know the type parameters of a class, and the class is not yet completed, because completed would mean I look at all the members and enter them. And in that case, I can actually look at the declarations of the completer and pick out all the type members that represent type parameters and return those. Okay, yeah, and then that one here, the stub info, that's essentially, if I hit a missing reference when I load something, I could fail immediately with an exception, but both Galassi and Dotty, they're nicer. They sort of make a stub and give you an error and continue with the thing. Okay, member names was that's then basically all the caching stuff that is sort of the end of this thing. That's all internal stuff, how it works. Okay, are we still fresh enough for quick denotations? And I speed up a little bit. Is that okay?
For what?
To cover denotations. It's not as long as sim denotations, and I think we covered most of it already.
Yeah.
Okay, so let's do that and finish for today. So
Okay.
so a denotation is, is a sim denotation or a reference to one, and it contains, let's see, what does it contain? it contains some stuff to disambiguate. For instance, if it's overloaded, then you can find out what its alternatives are. So each of those are single denotations. You can find out what alternatives match a certain predicate. You can essentially disambiguate, that's a such that, which says, well, give me a predicate from simple to Boolean, and I give you a single denotation. So that would fail if it's after the disambiguation, it's still ambiguous, and so on. Find member is, we've seen already. Disambiguate is essentially like such that, but yeah, it's all in the comments. Okay, so there's some things that are sort of mostly used for loading things and definitions. So I can typically have a required method, so that gives me a string. A prename is a string or a name. I can ask for a method or a method ref, I can ask for a method given a name or a name and types. I can ask for a value, so not a method given a name. I can ask for a class given a name, and so on. So most of these things are used in definitions. Here, there's a bunch of them here. So here, now, yeah, here you see required class, required method ref. A method ref is essentially a term ref referring to a method. And you see a bunch of them here that use all these things. So that's just how you pull in sort of predefined stuff. Okay. So matching denotation, that was partly used for the overloading for overriding, so that you say, well, I need a matching symbol in this base class. So that's essentially that's overloading resolution, that we say if we have a denotation which is overloaded, so has several alternatives, then the alternative that has a type that matches target type. Okay, good. And now we come to the interesting bits of denotations. So we've seen pre-denotations, which are essentially just a bag of hits. So now I have to sort of consolidate them into a single denotation at the end. Once I collected them all, I have to consolidate them. And so the reason why I deal with pre-denotations is that they're more cache friendly. So because I say, well, essentially I have a bunch of pre-denotations in a superclass here and here, then I form just the union, that set union. But if I would have already a join type in each of them, then that join type I would have to throw away and recompute, because I might get more alternatives and things like that. So that's why I have pre-denotations, but at some point I have to make a denotation out of them. So essentially for that I need this join thing, which says, well, I have a denotation and I have another denotation which maybe came from two parents, and now I need a denotation that's both of them. And that's a very tricky thing, how to do that. So let's see. But here, so it says, well, if it's the same denotation, then that's okay. If one of them is a no denotation, so that means it doesn't exist. So exists is typically a thing that we have on many things, which means it's different from the no XXX sentinel. So if one of them is a no denotation, that's simple. Pick the others. If we have a single denotation, then essentially we have this problem. Then if we have two multi-denotations, then we have to essentially pick things that sort of are the same alternatives and merge those. So that's the hard part about it. If you have two single denotations, it's easier. Maybe let's look at this case first. Yeah, so that's merge single denotation. So that just takes two single denotations and says, well, make a denotation. As you can imagine, it's very performance sensitive. So we try to sort of keep things as simple as possible and do stuff only when we must. So basically what we need to determine for the new denotation is what's its symbol, what's its info. So that's so what's its info is essentially used as an alternative of type. So basically we use an info instead of type to say denotations can be terms, and terms have types, and they can also have types, and essentially the type of a type, that's its bounds and kind and things like that. And to have something that essentially can be either, so either the type of a term or the bounds and kind of a type, that's called in the fields an info. Its type is still a type, so because types describe everything. But if we want to make clear that this is the type information for either a term or a type, we use info. Okay, so we need to define the info and the symbol for this new denotation. So let's see, what do we do? So we say, okay, if the first thing is the symbols might actually not be accessible. So we've seen accessibility like it's private, or we're not supposed to see it. So in that case, we should discard the denotation because we shouldn't be seeing it. So if the symbol is accessible and we prefer it, then over the first one, so that's sort of the disambiguation, which of the denotations we should prefer, then pick the second denotation. Otherwise, if the first symbol is accessible and we prefer the first symbol and info over the second symbol of info, pick the first denotation. Then we say, okay, if the first is accessible and the second is not, then pick the first. If the second is accessible and the first is not, pick the other. So these are all things. Then it could be a double definition. That means that in the same scope with two symbols, then we have to handle that specially. And otherwise, okay, so that's sort of then the tiebreaker, that we say we have to essentially pick the symbol. We can't pick either one denotation, which is of course preferable because we don't have to allocate a new object. So now we have to make a new one, and that's where we get a joint ref denotation. That's where we have to sort of combine the two. So we have to decide what symbol we pick. So if one doesn't exist, that's easy, and then there's a preferred symbol thing, which sort of is a tiebreaker. And for the infos, we we use essentially an AND type, a conjunction. So that's what this info meet thing is. Oops. Right. So what the info meet is essentially, it's a bunch of things that could all happen. So and the problem here is that not all combinations are actually legal. For instance, if I have, let's make it here, trait A, class C, trait B, class C, and then I want to say what's the info of A and B, hash C. What's the info of that one? And the answer is I don't have one. There is no info because that's an illegal situation. Here I can't form the conjunction of two class definitions. That's not possible. So I get a merge error in this case, and that's a merge conflict. So there are some things when I get code from Scala 2, because Scala 2 doesn't have that, it will just do one thing or another. One isn't probably very sure whether it's the right thing, but it will just do something. That you get these merge conflicts and merge errors, and that's then unfortunate, and you need to sort of handle this somehow. But it's one of the porting problems from Scala code. Let's see what merge conflict actually is. So it will give you an error called cannot merge, and then essentially it has the two types. So this would probably say A hash C with B hash C in one type. So that's what it would say here typically. And that's an error condition. So it actually throws it. A merge error is a part of a type error, I think. Oops. No, now my IDE is acted up. So a merge error is a form of a type error, and there's a thing in the typer that catches these things and converts them to error messages. Okay, good. So we sort of did a deep dive in this merge error thing here, and that basically that's what the join of two denotations leads in the end to the join of the two types, and that essentially handles these things which are tricky, and otherwise in the end, so that's sort of the most common case, if all these special cases are dispatched, which is it's a join, it's an end type. Yeah, here we have the problem that if there are two method types, then something like this, that's also a problem, because we can't really form a merge of a polytype, so polymorphic method type with a method type. We can't merge them point by element. So here, for pragmatic reasons, we prefer one over the other, the method type in this case, which is not good, but yeah. Okay, so that's sort of the thing here, right? So that was what the merge thing is, and then there's another one which says, okay, if these things are what did we have? That was the informate, yeah. If we have multi-denotations, then we sort of have to look at all the cases, and yeah, and if we essentially we check all possibilities, we overlap them all. If they match, so that means the same signature basically, then we merge the single denotations, and otherwise if we give you a no denotation, because we can't merge a thing which essentially two methods that have different overloaded alternatives, to join them, that would give you not something that's valid. Okay, so that was sort of the main complexity of the denotation merging. There's another one which is sort of a dual of that, which is to say, well, if we have here an OR type, so A or B, and we want to give you the denotation of that in the OR type, then that's what we would have. It's pretty much the dual of the end. Okay. And then finally we have here the multi-denotation, which is essentially the thing that is this big bag of simple denotations, and that's basically only used in member lookup. So when I do member lookup in the caches, I have these pre-denotations, and then by the time I actually have a denotation, then well, no, then I can still have a multi-denotation. Then then I still have a multi-denotation, but I have to disambiguate that with overloading resolution. That's what that does. Okay, and then I have a single denotation here. That's the final thing. So that has essentially all the things that I've seen at denotations. That's mainly an overriding thing here. Okay, yeah, and then we have this thing. Did you cover that? Bring forward and the stuff?
I covered the idea.
Yeah.
I didn't go into hard cases. I covered what it's intended to do.
Okay.
So I didn't explain how it reloads parents, for example.
Okay, yeah, right. So that sort of is the fact that you have a denotation and it's valid at some phase, and then you want to say, well, what would this denotation look like at some other phase? So that's this current thing, which gets a context, and the context contains a period in which it should be valid, and that essentially will, by going through the info transformer, adapt the denotation until it's found, until it's in the current one. So what that does is it says, okay, if the denotation was defined in a previous run, so that's the incremental compilation, then we have to do something called bring forward. So essentially we have to look whether it's still valid in the current run. Otherwise, if it's defined in the current run, then we have to go through our ring of all the possible denotations with the info transformer, which gets constructed lazily, so we have to build them if we don't have them yet, and essentially look at the version of this denotation at the phase given by the context. So that's another thing which is, of course, very performance sensitive and therefore written in a very low-level style and very try to optimize as much as possible. Okay, bring forward essentially says whether a denotation, whether I can essentially reuse a denotation that I've gotten from a previous run. So, for instance, here in the editor, every time I press a key, I get a new run. Whether I can use a denotation in a new run, and the way it does that is essentially it crawls up the owner chain, and when it hits a top-level class, then it says, well, is that still the same top-level class from the last run? So nobody has edited this class, and then essentially all the symbols in that class are still valid. And if not, then that's bad. Then I just referred to an inner symbol of a class that doesn't exist yet, and I get something called a stale symbol error. So that's an exception that says the symbol is stale, and that shouldn't happen. Unfortunately, it does sometimes. But you get exceptions, and we're tracking those. Okay. Right, and then we have these installed after transform after. Yeah. Okay, I think that's pretty much it. And the rest has to do with pre-denotations, and that's just essentially using. No, that's just up to here. That's also good. Yeah, and then here you see the unique ref denotation and joint ref denotations. That's basically just data types. They just contain essentially a tag, what they are, and they contain a symbol, a type, and as all denotations, a period where they're valid. And so that's init valid for. So the period where they're valid it has an initial creation period, could be just a single phase and run ID. But then when I sort of look at it at a different one, then I look at all the transformers that are there. But a transformer could say, well, no, this denotation hasn't changed, and then essentially I don't make a new copy of the denotation. I just extend the validity period. So these validity periods, as I explore things, they can grow. Yeah, and I think that's pretty much it. Oh yeah, as seen from, yeah, we have to go through that. No, not all of that.
So because of this optimization, when we extend the denotations, sometimes we need to also split them. So if you enter a symbol into a denotation, and denotation is spawning over multiple periods, and you enter a symbol in the middle of it, you'll have to split it because in the first part it doesn't exist, and then it starts existing.
Yeah.
Okay.
Okay. Another
So
thing
this is reducing a validity period.
Yeah.
Okay.
So another thing that just to explain the layout. So a bunch of these traits, I haven't really paid notice to that, has things like that. So it's essentially a thing and then base, and they are essentially, their self-type is a context base. So that's essentially the context is what carries everything. We haven't looked at it yet, right? So we need to do that.
No, we didn't.
We didn't, yeah. So, okay, so there's still things. So I remember flags, names, context. So that's sort of the more lower level things that we need. Well, context is really higher level. So a context is basically that's the implicit that I pass virtually everywhere, and that contains everything. So that's sort of compared to the previous Scala 2. That's what replaces global. Global was the thing that bound everything together. That was this huge cake. And there's a bunch of stuff that's defined directly in contexts, but there are some things that are sort of better defined together with an abstraction, and so they are essentially defined in traits that get inherited from context. So these things are all part of context. So, for instance, to call static ref, that's essentially a static reference given by a path name, I would then write ctx.staticref, because if it's defined in denotation space, then it's a part of a context of the current context. So that's how I get at these things. And I think there's some in sim denotations and in symbols as well. maybe just to finish this, do symbols, and then we're done with this. What do you think?
Symbols are small.
Symbols are small, yeah.
And they don't have
So
any-
is static ref like a path that starts at root?
Sorry?
Is a static ref like a path that starts at root?
That's right, yeah, yeah.
Okay.
Yeah, you give it a path constructed at root. So the required symbol, the required method, required field, required module, required class, they all use static ref in the end, yeah.
Yeah, okay.
Okay, so finally symbols. So symbols are the sort of the thing that we said, no, this is not a symbol, that is not a symbol. So finally, what is a symbol? So like I said, a symbol is basically a single definition. And here we have again the parts that is essentially from a context. So I can do create a new symbol with essentially ctx.symbol, new symbol. Right, so that's what they do here, and there are a bunch of symbol creation methods that that will do this. So that's the most general one. New symbol. Then I can create a new class symbol that would contain essentially here, because again with recursion, also for new symbol, for new class symbol, I can't give you the type, because it typically refers back. So I say, well, create the symbol first, and when you're done, then I have a function that, given the symbol that you just created, I come up with the type of that class symbol. So that's why it's not an info, but an info fn, so info function that's given here. And there are a number of others. So in some cases, I don't need to do that because the type is simple and doesn't refer to the class. Then I have new complete class symbol that does it. So there I can just give there I don't even give the full type. I just give the elements of a class info type. Those are the parents. So what are the parents? What are the decals? What's the self? And yeah, that's the three things that make up a class info type. Okay. Module symbol. That's a more tricky thing, because as you've seen with the decomposition, modules really decompose into module classes and module values, so lazy vals basically. So that thing actually gives you the module value, but it creates the module class sort of next to it, side by side to it. So it gives you both. You can get then from the module value to the module class as usual with .module class. Okay, and there's sort of there are all these things, and you can create package symbols. A stub symbol, like we said, is a symbol that essentially is missing. So a local dummy is so that's a bit tricky. Yeah, good to explain it. So if you have a class C and we have a val-x, what's the owner of x? Well, it's C, right? But what if we have a val y here? To say the owner of y is C, that would sort of hide a crucial difference. To say, well, the x is a field of the class, but the y isn't. It's inside essentially the primary constructor of the class, but in the primary constructor of the class, we don't want to say that either, because that sort of is the parameters. So instead of the primary constructor, we make up another symbol which is called a local dummy, which is essentially the thing that corresponds, that is the inside of a class before we have created the constructor that contains all these things. And that's the owner of y. So that's a local dummy here. An import symbol, so that's essentially a symbol representing an import. Constructor, that's a primary constructor or secondary. Synthetic lazy implicit value, you don't need to know that unless you look at what we do with lazy implicits here. A self symbol is a symbol representing a self-type declaration. So if you have a self and then some type T, and that essentially gives you implicitly a symbol declaration. That's the self symbols. And then there are ways to create, given from a class, type parameters for the class, scholems, and then we have tricky operation map, but for that we really need 3 type maps. Did we do that?
No.
No, oh shit, one after another. Okay, I skip it for now. Okay, cool. And these are, we've sort of seen them already in denotations, but they're also something where you can then just say it's context.required package and things like that. Okay, so what is a symbol then? A symbol has essentially nothing in it. You create it just with, what does it have? It has a position, and it has an ID. So the ID is just a unique ID. So every time we create a symbol, we bump the ID by 1. And one thing that's useful is when you really don't know what's going on and you're deep in debugging. So first thing is when you're wondering what happens, turn -unique IDs on. Minus unique IDs. So that's a command line option, and that will essentially give every symbol with a hash and the ID of the symbol that you see here. And then when you want to say, well, where was this damn symbol created, then uncomment this assert and add the ID that you're looking for, and you get a nice stack trace by the time. So sometimes that's your last resort to say, well, where does this symbol come from? So here you know where it comes from. Okay, so that's why these IDs are, they're used also for like hashing and contains, but that's sort of for a compiler hacker, that's their most important use. Okay, and what they have internally is a denotation, and you can set it with a setter here. So as you create symbols, because they again can be heavily recursive, where do we have the one new normal?
New naked symbol.
Yeah, new naked symbol. That was
the first one.
It's the first one? Oh, I must have skipped it. Oh yeah. Okay, so what we typically, all the others, they essentially come down to say, well, create a new naked symbol, which essentially just gives me a coordinate, which typically is a position, and the next ID, which I get from the context, so that just counts up, and that gives me a symbol, and then afterwards I have a symbol to essentially hang on to, and then I can patch out the denotation later on. Coord, just to go to that, a coord is essentially a value class of an encoding of int, and it can be essentially a position or an index. So typically these symbols, if they come from source, they have a position, and a position is again encoded in an int. So the coordinate is can be converted into a position, and if they come from a class file, then typically they have an index into the class file. Like I am symbol number 123 of this class file, and that's then the coordinate of the symbol. So that's sort of an internal thing to figure out what they are. Okay, let's go back to what's in a symbol then. So the most important thing in a symbol is a denotation. That's here. So denotations are cached, as you would guess, in last denote. So to figure out what's the denotation of a symbol, essentially you say, okay, first let's see whether the current, the last denotation is still valid in the current period. If that's the case, then just take the last symbol, otherwise update the last symbol. And that then goes to this current method that we've seen in denotation. So that would then say, well, what's the symbol, the meaning of the symbol in the new phase of the context. Okay, so that's that way we get the denotation, and then we have just a couple of things where we don't want to force the denotation again to avoid cycles. So we try to figure out whether this is a term by just going to last denote, because as we change denotations, we will never switch terms to types, so we can just figure out the last denotation instead of the current denotation to figure out whether it's a type, whether it's a class. That's easy, only class symbols are classes. And right, and then the other thing I can do with the symbol is I can enter it. So we have already seen the method, so that was class.enter symbol, cls.enter symbol, right? So that enters the symbol as a member of a class, but I can equally well and shorter write just sim_blah.entered, because after all the symbol has an owner, so I know in which class it's supposed to be entered, which is always the owner of the class. So that's that entered method here, and that right, and that does one thing right, that if I enter a module, then it will enter the module class together with the module as a nice side effect of that. And then I have this entered after that I was looking for, and that's essentially when I'm in a transform, and I shouldn't do entered because that's a side effect. I should do entered after and say, well, that's essentially my current phase, and say after the current phase, this symbol that I'm just about to make up, create a new, should be entered. Okay, I have a thing or else, which a bunch of things have. So that just says, well, if one of the, let's say I look at a symbol here and there, and if I don't find it, it's a no symbol, then or else is useful. It's just essentially, it's like get or else on options to say, well, give me that symbol or else that symbol, the other symbol if the first one is a no symbol. Yeah, filter, name. Yeah, and then the other thing so the name is of us, right? So symbols, there's some type safety here that term symbols have term names and type symbols have type names. So that's done with this thing. And the last thing that symbols have, but denotations not, is the associated file. Because that's sort of, for a definition, that's always the same file. The definition comes from the same file, and all the denotations get that. So for a normal symbol, I go in the top level class, and I look at the symbol of that one, and I look at the associated file of that one. And in the class symbol, that's going to be overridden what associated file is, yeah. And the associated file can be a binary file, so a class file, or it can be a source file. And so that's depends if the symbol is loaded from source, like I'm compiling it currently, or I only find the source but not the class file, then it will be the source file, but if it's loaded from class, it will be the class file. Okay, and then here printing, we have a bunch of things that sort of toString gives you the symbol itself, but then there are other things that print it in various ways. So show located is something that is often used, that gives you the symbol and where it was defined, so the owner. Sometimes that's good for figuring out where things are defined. Show decal shows you essentially the symbol as it was defined, so it doesn't give you the name of the symbol, but it would say def f or class f, something like that. Show kind shows you whether it's a def or a class or a type or whatnot, and so on. Okay, so then the other one is for class symbols. We have one more thing that is if retain trees is set, then it gives you the tree that defines the class, so either from tasty or from source again. We could actually do this, add this to other symbols as well. I'm not sure whether we should. It's a potential space leak, that's why we haven't done that. And for an associated and for a class symbol, you see the associated file I actually give to the class. So a class symbol has a coordinate, an associated file, and an ID. Okay. And then I have a decorator called copier, which copies a symbol. That's also sometimes useful, where essentially I take a symbol and I can essentially give it arbitrary info, so owner, name, flags, info, private within, coord, or associated file. It would just give me a new symbol, which essentially contains the new fields as given and the other fields from the current symbol, and that takes care of creating either a class symbol or a normal symbol. And oh yeah, the other one, that's sort of, you see a bunch of things, defen, right? So for instance, defen.any class, so you might wonder, well, what is this defen thing here, definitions? That, like everything, is context dependent, but we have here essentially a method defen of an implicit context, and that's essentially the current definitions in the context. So defen is sort of the recommended way to represent, to refer to things that are in this big definitions object, which contains essentially all the predefined things that the compiler is supposed to know about. And that was it, I think. Yeah. Okay, any questions?
Any questions?
Any further questions? You asked already quite a few.
Yeah, I mean, I guess there's some topics that we didn't look at, but I think we should save those till next time.
Yeah, indeed, yeah. So, and they are fairly shallow. So I think we went through all the key abstractions. What we didn't cover was names. So, like I said, they're now semantic names. So essentially, they have a structure that represents sort of what they mean in the compiler. Contexts, which is essentially just a bundle of everything that anybody might want. Flags, which are these, we have already seen some of them. So I guess we can just quickly browse through them, but not for this time.
Mini phases and helpful APIs.
Yeah, so should we leave those things to another?
Okay, let's do
another
one.
episode.
I guess so. Yeah, I think we might need one more, and then we should be done with it. I imagine.
Yeah,
You can always find more stuff.
We can always find more stuff. Yeah. Yeah.
In addition to that, it would be interesting to hear a bit about the type inference and the typer itself.
Oh, the typer and type inference. Okay, yeah, that will require its own session. I guess several. So I guess we need the typer, and we need the and then there's the implicit search, which is its own chapter, I think. Oh, and subtyping. Yes.
Okay.
Beautiful. Yeah.
3 more chapters.
So I mean, as you go through it, it's actually. I mean, there's so many interactions and things like that. It's actually quite surprising that it's so fast, no? And I think it's only so fast because we were very careful to say in all these caches we have sort of a short path, and often the short path actually can get inlined by the JVM, and so some of them I actually counted the bytes to say I want to make sure it's under 35, so that the JDK will probably likely inline it, because otherwise it's not good. And it turns out that it seems like the other thing is that where we lose speed is mostly in memory bound, so probably that's why all this computation in the caches actually doesn't matter, because it sort of gets compensated by a stall for memory somewhere else or something. Yeah.
Well, as long as we don't hit it randomly, it will help. But because we hit it randomly.
Yeah. That's right. Yeah. But I think there's a lot. As you see, there's a lot of interaction. Like if I want to go from a type, I have to actually look up the symbol of the type with the computation, and I have the symbol, but to figure out what it means, that's another lookup, and these sort of things. So.
Yeah.
Yeah.
Okay.
Okay. Cool.
Okay. Thank you very much. Thanks
Thank
a
you,
lot.
Andre.